Hello guys, and welcome back. Today is part 11 of the AC motor control methods. Today we're going to talk about variable speed AC motor control. We're going to talk about the different methods of changing the speed of induction motors. Discuss how an alternator is used to provide variable frequency motor control. We're going to talk about the electronic methods of variable frequency controls. Two factors that determine the speed of the rotating magnetic field of an AC induction motor are: first, number of stator poles; second, frequency. If either of these factors is changed, the speed of the consequent pole motor can be changed by changing the number of stator poles. This method of speed control causes the speed to change in steps and does not allow control over a wide range of speed. For example, the synchronous speed of the rotating magnetic field in a two-pole motor is 3600 RPM when connected to a 60 Hz line. If this motor is changed to a four-pole motor, the synchronous speed will change to 1800 RPM. Notice that this method of speed control allows the motor to operate with a synchronous field speed of 3600 RPM or 1800 RPM. The motor cannot be operated with a synchronous speed between 3600 RPM and 1800 RPM. Variable voltage speed control. Another method of controlling the speed of some AC induction motors is by reducing the applied voltage to the stator. This method does not change the synchronous speed of the rotating magnetic field, but it does cause the magnetic field of the stator to become weaker. As the magnetic field of the stator becomes weaker, the rotor slip becomes greater and therefore causes a reduction in motor speed. Variable voltage speed control is used with fractional horsepower motors that operate light loads such as rains and blowers. Motors that are intended to be operated with variable voltage are designed with high resistance rotors, such as the Type A rotor, to help limit the amount of current induced into the rotor at low speed. Induction motors that use a centrifugal switch cannot be used with variable voltage control. This limits the type of induction motors that can be used to shaded pole motors or capacitors, the starved capacitor run motors. There are several methods used to control the voltage supplied to the motor. One method is to use a triac with a phase shift network similar to the circuit. When triac circuits are used with inductive loads, care must be taken to ensure that both halves of the AC waveform are conducted. Only triac controllers intended to be used with inductive loads should be used for motor control. Triac circuits intended to control incandescent light loads will often be conducted on one half of the AC cycle and not the other. For example, assume the triac in the above image from Doug's on the positive half cycle of voltage before it conducts the negative half cycle. A waveform similar to the one to be produced across the load. Since only positive voltage pulses are being conducted, the voltage applied to the load is DC. A DC voltage applied to the resistor load, such as the incandescent lamp, will not cause any harm, but a great deal of harm can be done if a DC voltage is applied to an inductive load, such as the stator winding of a motor. Another device used to control the voltage applied to a small induction motor is the autotransformer. A rotary switch is used to connect the motor to different tabs on the transformer windings. This allows the motor to be operated at any one of the several different speeds. A tapped inductor can also be used to control motor speed. The inductor is not used to control the voltage applied to the motor, but is used to control the impedance of the circuit. If more of the inductor is connected in series with the motor, the total impedance of the circuit is increased and therefore the current flow through the motor is decreased. The current flow through the motor is decreased. As current flow is decreased, the magnetic field of the stator becomes weaker, and the increase in rotor slip causes the motor speed to slow down. The motor speed can be adjusted by changing the tab with the rotary switch to insert more or less of the inductor winding in series with the motor. Variable frequency control. One of the factors that determines the speed of the rotating magnetic field of an induction motor is the frequency of the applied voltage. If the frequency is changed, the speed of the rotating magnetic field also changes. For example, a 4-pole stator connected to a 60 Hz line will have a synchronous speed of 1800 RPM. If the frequency is lowered to 30 Hz, the synchronous field speed falls to 900 RPM. When the frequency is lowered, care must be taken not to damage the stator winding. Current flow through the winding is limited to a great extent by inductive reactance. When the frequency is lowered, inductive reactance is also lowered. XL equals 2 pi FL. For this reason, variable frequency motor controllers must have some method of reducing the applied voltage to the stator as frequency is reduced. Alternator control. One method of producing variable frequencies for operating induction motors is with the use of alternator. In this arrangement, some type of variable speed drive, such as the DC motor, is used to turn the shaft of the alternator. The speed of the alternator determines the frequency of the voltage applied to the induction motor. The alternator can furnish power to as many induction motors as desired, provided the power rating of the alternator is not exceeded. Since the output voltage of the alternator is controlled by the amount of DC excitation current applied to the rotor, a variable voltage DC power supply is used to determine the output voltage of the alternator. As frequency is reduced, the output voltage must also be reduced to prevent excessive current flow in the windings of the induction motor. This method of speed control is frequently used on conveyor systems where it is desirable to have a large number of motors controlled from one source. Solid-state control. Most solid-state frequency drives operate by first changing the AC voltage to DC and then changing the DC voltage back to AC at the desired frequency. For example, a variable frequency drive uses a 3-phase bridge rectifier to convert three-phase AC voltage into DC voltage. If phase shift unit controls the output voltage of the rectifier, this allows the voltage applied to the motor to be decreased as the frequency is decreased. A choke coil and capacitor bank are used to filter the output voltage of the rectifier before transistors Q1 through Q6 change the DC voltage by decreasing. An electronic control unit is connected to the base of the transistors Q1 and Q6. The electronic control unit converts the DC voltage back into three-phase alternating current, returning transistors on and off at the proper time and in proper sequence. For example, assume that transistors Q1 and Q4 are switched on at the same time. This allows T1 to be positive at the same time T2 is negative. If conventional current flow is assumed, current will flow through transistor Q1 to T1, from T1 through the motor winding to T2, and then through transistor Q4 to negative. Now assume that transistors Q1 and Q4 have been turned off, and transistors Q3 and Q6 have been turned on. Current can now flow through transistors Q3 to T2, from T2, the motor to T3, and through transistors Q6 to negative. Since the transistors are turned completely on or completely off, the waveform produced is a square wave instead of a sine wave. Induction motors will operate in a square waveform without any problem. Some manufacturers design units that will produce a stepper waveform. Control using SCRs. Because of their ability to handle large amounts of power, the SCRs are connected to a control unit which controls the sequence and rate at which the SCRs are gated on. The circuit is constructed so that SCRs A1 and A2 are gated on at the same time as SCRs B1 and B2 are gated on at the same times. Inductors L1 and L2 are used for filtering and wave shaping. Diode 1 through diode 4 are clamping diodes and are used to prevent the output voltage from becoming excessive. Capacitor C1 is used to turn on the set of SCRs off when the other set is gated on. This capacitor must be a true AC capacitor because it will be charged to the alternate polarity each half cycle. In a converter intended to handle large amounts of power, capacitor C1 would be a bank of capacitors. To understand the operation of this circuit, assume that SCRs A1 and A2 are gated on at the same time. Current will flow through the circuit as seen in the following diagram. Notice the direction of current flow through the load and that capacitor C1 has been charged to the polarity shown in the image. Recall that when SCR has been turned on by the gate, it can only be turned off by permitting the current flow through the anode-cathode section to drop below the holding current level. Now assume that SCRs B1 and B2 are gated on. Because SCRs A1 and A2 are still turned on, two separate current paths now exist through the circuit. The negative charge of capacitor C1, however, causes the positive current to C8 path more negative than the one through SCRs A1 and A2. The current now flows through SCRs B1 and B2 to charge capacitor C1 to the opposite polarity. as seen in the image. Because current now flows through SCR B1 and B2, SCRs A1 and A2 turn up. Notice that the current flows through the load in the opposite direction, which produces alternating current through the load, and that capacitor C1 has been charged to the opposite polarity. To produce the next half cycle of AC current, SCRs A1 and A2 are gated on again. The negatively charged side of capacitor C1 will now cause the current to stop flowing through SCRs B1 and B2 and begin flowing through SCRs A1 and A2. The frequency of the circuit is determined by the rate at which SCRs are gated on. Features of variable frequency controls. Although the primary purpose of a variable frequency drive is to promote speed control, for an AC motor, most drives provide function that other types of controls do not. Many variable frequency drives can provide no speed torque characteristics that is so desirable in DC motors. It is this feature that allows AC squirrel cage motors to replace DC motors for many applications. Many variable frequency drives also provide current limiting and automatic regulation for the motor. Current limit is generally accomplished by connecting current transformers to the input of the drive and sensing the increase in current as load is added. Speed regulation is accomplished by sensing the speed of the motor and feeding this information back to the drive. Another feature of variable frequency drives is acceleration and deceleration control, sometimes called ramping. Ramping is used to accelerate or decelerate a motor over some period of time. Ramping allows the motor to bring the load up to speed slowly, as opposed to simply connecting the motor directly to the line. Even if the spin control is set to a maximum position, when the start button is pressed, ramping allows the motor to accelerate the load from 0 to its maximum RPM over several seconds. This feature can be a real advantage for some type of loads, especially gear-driven nodes. The amount of acceleration and deceleration time can generally be adjusted by setting potentiometers on the main control board. Some other adjustments can usually be set by changing potentiometers as follows. Current limiting. This controls the maximum amount of current the drive is allowed to deliver to the motor. Volts per hertz. This sets the ratio by which the voltage increases as frequency increases or decreases as frequency decreases. Maximum hertz. This controls the maximum speed of the rotor. Minimum hertz. This sets the minimum speed the motor is allowed to run. Again, thank you guys for watching. I hope you guys like this video. Again, like, share, and subscribe. Feel free to comment, and we'll see you on the next one.